So I'd just like to invite back all our, thank you, Oliver, first of all, and I'd like to invite back all our speakers, please. You should now also all have the ability to turn your microphones on and off at will, and please just raise your hand or go for it when you'd like to respond. And we'll just spotlight you all so you can all be seen. So I think just to pick off where Oliver left, really, as a panel, what are your thoughts on this idea of combining these two different computational paradigms? And does it answer Rebecca's question? Was she therefore showing morphological computation without the standard memory and ALU kind of computation? And therefore, can we say that these non-autonomous human-in-the-loop robots still show embodied intelligence? Anybody want to start off discussion?
It totally depends on what we mean by embodiment, right? So what is the boundary of the embodiment? I mean, in my view, there's no boundary. So for the brain, the whole body is the environment, right? And for the fingertip, the rest of the body is the environment. So there's no boundary. So in Rebecca's case, I think both the robot and the human were embodiments.
I think this is interesting. Whether is the environment part of the system, because one of the things we see in all these embodied intelligent systems is the coupling with the environment. They have this environmental niche, be it in water and air. So there's we've got to have this understanding of is the environment part of the body, and how does that also sit into our kind of discussion?
I think it's just an orchestration of a symphony of everything. I don't know.
But I mean, if the environment, I mean, I agree actually that the environment is critical, right? And intelligence without environment doesn't make any sense. But if the brain is the body, if the body is the body, if the environment is the body, then everything is the body, and that means nothing is the body, right? That word becomes completely meaningless. It's just synonym for everything. So if we want to kind of make progress, we need to peel apart the layers of the onion. And I think one first step in doing that is to separate the phenomenon of intelligence from the phenomenon of different computational paradigms. You can combine computational paradigms without being intelligent. And so what I'm claiming is not that once you have morphological computation and traditional computation combined, you're automatically intelligent. What I'm saying is if you want to devise an intelligent artifact, you must combine different computational aspects because that gives you the power that is required to become intelligent, to behave intelligently.
Rebecca, how do you feel this fits into your kind of scheme of morphological computation and not? Does it?
Yeah, I was just considering like whether I want to say anything. So Oliver, I know. So Oliver, I wish I had seen your talk before I made mine. I like your definitions better than more than what I proposed. And I think I agree that the examples I show, if I'm trying to draw a clean line through it, I think the examples I showed are probably more examples of morphological computation and less examples of embodied intelligence. And I also, what you're saying resonates with me because as I was putting together this talk and kind of digging through all of these definitions that people have put forward in the literature and other places, I have to admit, I became really confused about all these different definitions because it seemed very vague to me. It seems like it's this symphony, as we say, of the brain, the body, and the environment, but that's everything, right? Everything exists with a body in an environment, and so then where is the intelligence? And that's why I kind of started focusing on defining intelligence and then trying to figure out how that fits with embodiment. So I don't think that I have total clarity still, but this is certainly helping.
I think Rodney Brooks at some point said that intelligence is in the eyes of the observer. So it is, I mean, relative to how we see this, right?
Do we need a definition? Is this half the problem in trying to box it up and actually put a definition of it? We're taking something that's everything and nothing and kind of formulating it into these very kind of box-like structures. are we actually having, and it's emergent, there's things that we couldn't yet classify and say this is the reason. Is this the wrong thing that we're trying to do to describe it, to come up and force definitions on it?
Well, I think definitions need to come natural, right? I think if we're trying to define something and we fail several times, then maybe we should say we're not ready for that kind of definition. Let's focus on, it's like the zone of proximal development, right? You learn things that are just the next step. And so I think defining something like intelligence is very difficult and maybe futile at this point. But defining something like computation, this is something that we have done successfully, with different computational paradigms. And I mean, Dan was mentioning physics. I mean, physics is millennia ahead of us in that regard, in sort of really kind of formalizing a set of physical phenomena. But I think this is a beautiful point for this field, right? Because we have, I mean, all the talks. It was so exciting to see all the things. We're doing such exciting stuff, and we're just sort of a little bit like a kid in a candy store, right? We're like, wow, that works, crazy. But now I think the next step is to calm down again and to sort of take inventory of what we've done and to try to formalize that in some way.
So are we talking more of a methodology perhaps than a definition? Is it how we approach problems, how we approach understanding biology, and how we approach solving engineering problems? Is that actually what we're talking about creating, rather than trying to define something? Is that the direction we should be going in?
I think that's a very good comment.
Yeah, I think the fundamental thing is we know that there are biological beings that do super cool things, and then none of our robots cannot do them. We don't know why, right? And then we think, okay, 1980s they thought, oh, it is a computer's CPU problem. When we have faster computers, we will solve it. And then it didn't work, right? So when you have faster yes, I think Dan has something to say.
Yeah, I might add to this. This is very interesting, and from my 2 cents, we also have, it turns out, lots of robots that do things we have no clue why they do what they do. And I saw this most clearly again when I was working with Howie Joseph on developing controllers for limbless serially connected robots to go through lattices, right? And they said, okay, we'll try to maintain a shape, but we'll add some compliance, and then we'll vary this parameter and that parameter, and sometimes it works and sometimes it doesn't. Why? Who knows? And it really is who knows. And it's the sort of thing where the problems in control tend to be, in my opinion, problems that operate in relatively pristine environments and are successful in relatively pristine environments. When you start getting these soft systems interacting with weird environmental situations, this is what I was trying to narrate, there's just a whole bunch of interactions that we have no clue about. And so I would say that we're so primitive in I don't think there's it's just incredibly primitive on what we know, would be my take on all this. And we're fooling ourselves if we think. And in fact, this computation issue, Oliver, is very interesting. I don't know anything about computation other than programmed a little, but we've been working on a problem for years, which I just flashed up at the end. A few years now, I've had this sort of obsession with recapitulating aspects of fundamental physics and robots. And so we tried our quantum, but we also been mathematically more successfully, been able to map the interaction of robots driving on spandex deformable membranes to a more GR-like formulation. It turns out making the robots active is what separates that as a scientific system from the demos that one sees in science museums. One can do an actual mathematical mapping. I collaborate with a relativist on this. And so I started to think about this, and I started to wonder about, in some sense, the system, we're doing kind of a computation. You might have heard that there's this field called analog gravity, where people try to make laboratory versions of general relativistic situations. And that way, you're sort of simulating a complicated system, in part because you can't, in astrophysical situations, you can't do the kind of scientific poking and perturbation that sometimes we like to do. It's mainly observational. Yeah, but at some point, solving Einstein's equations digitally on a digital computer is just impossible. And there used to be a field of analog computation, as far as I could tell. And when I was an undergrad, we would build circuits solving ODEs by plugging R's and L's and C's in. And so I started looking at, well, where did analog computation go? And it seems like there's still some folks doing it.
Yes.
But digital computation basically ran roughshod over that. And folks who used to design electrodes by letting marbles roll on are gone. And the differential analyzer, which had all sorts of cool gears, and gone. And I think it's funny because our digital computation, maybe quantum computers will fix it, but our digital computation is also very, 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 very limited, particularly in my situation when it comes to, you know, modeling the environment. We just have no clue on how to model most environments, whether we should. So anyway, that's my 2 cents on analog computation.
I mean, and the fascinating thing is the neurons are so slow, right? So a signal from a fingertip to the brain takes about 120 milliseconds. And, you know, and then these sloppy computing elements. Of course, yes, we have 87 billion neurons in the brain. That's a parallel you can think of, you know, super parallel computing. But still, it doesn't explain the full thing, right? So with these slow computers, they deal with very real-time problems that you know, our computers and our robots cannot do. That is why we think like the passive dynamics and that kind of algorithmic computing should come together, and then they solve problems. Like the mountain goat hoof is one example.
Yep.
The hoof solving the local problem, the brain doesn't have to deal with, right? And in the ear, the cochlea solving the time domain to frequency domain mapping problem in real time, so that the brain can deal with frequency domain computing. So it's a shared computing responsibility taking between the body and the brain, and then we really don't quite understand how that happens.
Yeah, so it's a great example. I mean, we've been studying snakes and lizards and macroscopic organisms for years, and it just so turns out that a lot of the tools we've developed are transfer quite nicely, as I put in the spammed everybody in the chat, to the microscale, largely because most of our organisms turn out to be swamped by friction that dominates inertia. So everything is shape changes, and so it becomes geometric. So I started working on nematodes because as a model organism, you know, there's in principle lots of money, and more important, there's lots of tools which can get into the neuro circuitry. And, you know, everyone says the first thing you see is C. elegans is a simple system, you know. So you then go ask, well, what do people know about C. elegans in their natural environments? And the answer is very little, because mainly they're moving around in rotten, nasty materials. They only have 302 neurons, but as Pietro's talked, you know, you only need few numbers of metronomes to get beautiful emergent phenomena. But their body morphology, their tissue characteristics, their muscle morphology, they're all part of this incredible thing. And so it shocked my robotics snake robot collaborators to know that the nematodes are so much better than any of our snake robots in doing they work in the worst environments in the world. So again, that's, I guess my point is, we're so primitive in our understanding of the biology, and so it seems very premature to have a grand synthesis to me.
Pietro, just to bring you into this, having seen kind of from a robotics perspective how we're approaching this thing, this kind of question of embodied intelligence, what do you take away from it? Where do you stand? Do we need to understand this? Do we need to define it from a biologist, kind of a physics, biological perspective? Yeah. Where do you stand?
Well, I struggle with the definitions. I prefer this approach, which is a bit more engineering-like, or discovery of the sort of nature. It's more consonant to me. But to me, the most fascinating thing is really this bridge between the physical computation, the analog computation, and the digital one. And if you have systems like the one that I'm trying to develop, where you can sort of morph one into the other, then what you might end up having is sort of a digital computer, but it's still picking up physical signals, and it's still sort of morphable and malleable. So you might, if you're very, very clever, you might end up with a computer that doesn't always do the same computation, but is actually doing the right thing at the right time. So in some sense, I think the brain has evolved to do a lot of that, because it has many time scales, it's adaptable, it learns, it reinforces the synapses, etc. And but we could come up with alternative kind of engineered systems that have some of the similar principles.
Thank you. And Mirko, again, I think your robots perhaps are slightly unusual in the way they embody kind of intelligence in this way. Where do you stand on and how we should define it, and how your robots kind of embody this approach?
Thanks. So I think I completely agree to this, what Oliver said in the talk, which is that this discussion of body versus mind is so deeply ingrained in philosophy and our culture and religion and so on. So it's very easy to fall into that. However, I think, this is important for us as soft robotics community to define our stance on intelligence, right? And this is, I think, important to get some kind of statement that the embodiment, the body, the materials can have some level of contribution to that. But at the end of the day, I think we need to combine the two. We need to combine the brain with the body, right? The human works like that, an insect works like that. For example, a bee uses some higher level navigation using the sun or environmental sensors. It uses lower level controllers to deal with the lower Reynolds number aerodynamics and the interaction control with the environment. And then it uses the materials, functionalized materials, to, for example, attach to structures using some kind of adhesion mechanisms on the feet. So these kind of three levels of autonomy, higher level autonomy, lower level control, and then embodied kind of functionalized material, I think is what at the end of the day will give this revolutionary capability. So in our definition of physical AI, we put this in lifelike, where lifelike is this whole package of being able to deal with the uncertainty in terms of sensors, in terms of environment, in terms of its own body, and the healing of the body, the structural change of the body, the adaptation of the learning or the controllers with changes in the body as well. So all this together, I think at the end of the day, will be the highest capability if we can combine it. But it might take 20 years to do that as a field. But I think that can be very valuable.
So what should we be doing what should we be focusing on? Is it a matter of focusing on where can we find the areas where we can best combine this morphological computation with kind of von Neumann computation to find these kind of ecological or task niches where we can use embodied intelligence to make the most difference? Should we be trying to understand biology to reverse engineer it? How can we really advance this field forwards in meaningful and significant ways, and trying to find fundamental limits also for these different types of intelligence, to be able to scope out this kind of landscape of both physical, morphological, silicon-based computation? How do we make concrete steps forwards rather than just floundering in this very exciting but unstructured, unprincipled space? How do we make it a science?
I think looking at the entirety of these observations, like for example, we look at octopus and then take inspiration from octopus, and then we just forget that octopus is octopus in water. And then, I myself has done this mistake. Octopus inspired robot for surgery, and then it doesn't do anything, right? Because that inspiration doesn't work without that buoyancy in the water, right? So environment, we just take some inspiration and then forget about the environment and then think that is biological inspiration. It doesn't work. So we have to look at the entirety of the computing infrastructure and then not separate the environment from the body. So that is why I said where is the boundary, right? So it is very difficult to find that boundary. You find the boundary, and then that is very likely where we make the mistake.
I think, you asked exactly the right question, Josie. It's also very, very difficult to answer, right? But my sort of gut reaction to what you asked is, well, let's look at traditional computation. How did they do it, right? They somehow came up with models that characterize computation itself. Then they use that to characterize problems, right? There's all these different complexity classes. There's these levels, and they have these beautiful pictures that sort of tell you which problem takes how much time and how much space to compute, right? So they basically structured the whole space, given a particular model, the Turing machine, of computation. And so I'm not sure how to transfer that, but I think if we manage to do that, right, to really characterize what morphological computation is, and then to divide the world into categories, or the problems that we're interested in into categories, and say, you know, this is more difficult than that. I mean, that I guess would be the start of turning this into a science, but I don't know at all how to do that, right? Other than doing what we're doing right now, which is also great, right? I mean, we're doing the right thing. We're exploring, and we're learning in that exploration process, and eventually somebody will come up with a really great idea of how to connect the dots.
Yes, I think you're right. It's this connecting the dots is the hard bit, isn't it? It's how do we take these different ideas and as Thrish says, not getting stuck with just inspiration out of context. The context is so important, isn't it? It's this bigger picture that's really, really interesting. And just to tie back to our first plenary we had this morning, where he introduced this idea of this this Brooks juice. What's the missing thing that makes, for example, humans or animals have the intelligence we have? What, out to the panel, what is this, in your opinion, what is this missing juice? What are we missing that starts to have this huge discrepancy between?
I amplify that because it begins to sound a lot like vitalism to me, which is a little worrying that that's even being brought up. I mean, you know, emergent phenomena in dynamical systems produce magic without having understanding any of the constituent components. I mean, you know, I used to study pattern formation in sand. You take a bunch of sand grains and no one has the magic of a pattern, and you vibrate them in a thin layer up and down, and suddenly you get stripes and squares and hexagons with their own life. You know, when you start to bring in a magic juice, careful. I mean,
yeah, I agree. I think there's no juice and there's no magic. I think we know everything we need to know. It's like cooking, right? I mean, you can have all the ingredients at your house. There's no way you're going to make a 3-star meal.
And I don't, let me just put, I don't think we know a fraction of what we think we know. I think that that's part of the fun, is that, you know, yes, you may know something of the microscopics, meaning, you know, we know I like the video that Mirko showed, that, you know, of the robots falling over, right? That's fun to laugh at. But for me, actually, it's very interesting because each of those parts of those robots are so beautifully engineered and characterized and spec'd. And it's really the integration and the emergent aspects which we haven't clues. But this is a problem that cuts across fields, you know, from where I originally descend, condensed matter physics. That's been the order of the day, you know, that there are new phenomena that in these emergent systems that are not apparent at the level of, you know, the more microscopic version. You know, a walking robot is made of motors, but none of those motors walk. And so I think, you know, we may not even know the components. I think biologically that's very true. And even when we know the components, and I would say also that increasingly robotically, you know, okay, Rebecca makes a cool sensor, which she characterizes, but then you put it, or Oliver, your microphone example, you sort of know some of the properties of the thing, but then there's idiosyncrasies that come together. That's, I guess, my point in where the physics side of me, which is me, finds this stuff so fascinating. And that, you know, like Pietro said, there's a good bit of exploratory and phenomenological and experimental playing with the real world that I think is really important. And Oliver, I read the article you sent. I don't see that. I don't see the fruits of empirical based robotics, or whatever that was called, making it into modern robotics. Strong.
Oh, you should check out our work.
Yeah.
Can I say something that dovetails with Dan's comment? So I'm not even sure as humans we're that intelligent. If you look at sort of timescales of 5, 10 years, 50 years, and as we create cities, then we're doing the same job as termites and ants, really. But we're the same, or maybe actually not as good. Our stuff is broadly 2-dimensional, but our streets and highways get clogged with traffic jams that the termites would never do. So, and we don't have that system of the bees to sort of to keep our thermal circulation in the hive that we saw yesterday. We just we're not even very good at exploiting emergent behaviors. And we are subject to just stuff that we don't understand and ends up dominating us. So I think we need to be quite humble. There's perhaps a time scale and length scale on which we can use our intelligence, but things that are very fast or very slow, we just become agents where our intelligence doesn't even play that much of a role.
So can I just add to this? I mean, in terms of the juice, I think the juice is the brain juice of the researchers that build the robots, right? And in some way, in many ways in academia, it's much easier to be single disciplined expert on one thing. However, these things that we talk about here are between material science, control engineering, and mechanical engineering, biology. So it's quite difficult and takes a lot of courage actually to be between the fields. It feels very uncomfortable, right? So, so my kind of statement on that would be that we should have some kind of encouragement mechanisms, awards or similar, that can help people to explore being at the interface of disciplines. And this will give rise and life to new types of robots, that combine these different disciplines. So the skill development. And I think this needs a lot of courage, and it's not easy, and we are not there yet. And I think there is a lot that can be developed on that.
So the point I was trying to make earlier is that, of course, we're not there yet. I mean, that's the whole point. But I think the problem that we're facing is different in nature, right? This is the cooking analogy. We have all the ingredients, but we don't know how to combine them into a good meal. So I think that with what we know right now, if we knew how to combine things right, we could create robotic systems that would be much, much more amazing than the robotic systems that we have now. We just don't know how to combine things the right way. So this is kind of a shift, I think, and this goes to also what Mirko was saying, that we need to understand more what's in between the disciplines and how they can operate together, rather than being disciplinary and working in our individual areas and getting more and more into the detail. So and I completely support the idea of coming up with a prize or something, but I think it's much more fundamental. We need to have funding for that. We need to have journals and conferences for that, right? We need to really create a whole academic infrastructure around it, because otherwise people cannot get tenure, right? And then nobody will do it.
Thank you very much, Mirko and Oliver. I think that's a fantastic way to round up this panel discussion. Is we can make steps forwards, and we need to actually, as a community, do this, to bring these together, have events like this, as you say, create the methodologies, create the outlet, and also the communication and the interdisciplinary working to make it acceptable and the norm to work in these interdisciplinary fields. I think that's a really positive statement that we can make going out of this discussion. So thank you very much, everyone. So yeah, thank you once again to all the panelists, fantastic talks and really interesting discussion. And we'll leave you all for about a 12-minute break, and then we'll resume with our next plenary talk. So thank you once again to all the speakers.